Hi everyone, this is Eshagh speaking from London South Bank University, focusing on waste heat and mine water. And today I'm going to talk about the integrating waste heat and mine water for energy in a smart heating and cooling network systems. So this is the general heat recovery concept for extracting heat from a mine water in Barnsley, the location we are working on. So as you are aware, so we are going to extract the heat from the mine water and heat up the buildings to a heat network systems. And then after that, the thermally used water become cold and we can reinject it in another location in a different cold seams. And if you get lucky, like the location we are working up and you can find the source of waste heat, so they usually need cold water for their cooling purposes, and instead we can absorb the waste heat, which in this case is 7 megawatt of heat, to heat up the buildings directly. Or if we have extra heat in hot seasons, we can store that heat under the ground and use them later in the cold season when we need them. So basically, to understand the systems, we had to create a numerical model with all the physical properties and the initial conditions like the pressures, the heat distribution, and any physical properties. So to create that numerical model, at first we created a geological structure and investigated the mine workings in the Barnsley area. Then we went through the flow modeling, and at the end we created a thermal modeling to understand the heat distribution, the heat loss, and the storage time. So to begin with, we started with building a subsurface model by using the available data to understand the mine distribution under the ground. And the purpose of this model was to calculate the void volume and the capacity, in fact, and then to understand how the subsurface may respond to the flow and the heat transfer. Then we created a flow model. So that's a big topic. I'm not going through the flow model today due to lack of the time, but I'll be happy to answer your questions in Q&A. But basically, the reason for focusing on the flow model was to understand the flow behavior and the impact of the flow for injecting and abstracting and changing the pressure, and what would be the environmental impact. So that was the purpose behind the flow. But if I go directly to the thermal model, in this graph, you can see at abstraction point, we abstracted hot water for 6 months, and you can see the temperature differences in the area over the 6 months of heat recovery. So the top one, which is the constant layer, that's a shale layer below the Barnsley seam, which is not penetratable, so the temperature didn't change. But exactly in the cold seam where we abstract water, for the first one, the temperature was quite constant. And the reason is because the replacing water comes from the other sides of the same mine with the same temperature and same depth. So the temperature didn't change. But then after a month, the replacing water from the other connected seams arrived here and combined with the hot water, so we start losing the temperature here. But over the 25 years of keep doing heat recovery here, you can see even the shale layer or the other area far away from abstraction point, they've been affected after a couple of years and they start losing temperature. So the whole area might be affected when we abstract water for a long term. And our observation was, so we understood the higher abstraction rate means the higher heat loss as well. But how much heat we may lose? So it depends on the other source of the connected seams. So basically, during the flow modeling, we understood that the majority of replacing water, they're coming from the same seam, other parts of the same seam, or they're coming from the other connected seams. So rather than from aquifers. And because of that, imagine if you're connected to a very shallow seam directly with a temperature, let's say 8, 7, 9, 10 degrees colder than your hot source. So when the water arrives here and they mix together, you lose a lot of heat. But if you're connected to just another seam a little bit closer to your seam, and the temperature differences is something like 2 or 3 degrees, so you lose less heat. And the other question is how fast we may lose the temperature and for how long we can keep the heat under the ground. So this depends on different parameters. Some of the most important parameters is one, how big is your cold seam and the geometry of seam compared to the level of abstraction rate. And the other thing is your connectivity. So the connectivity is good. We usually drill a borehole close to the junctions or any connectivity because we want to get a better flow rate, which is quite wise. But we have to be aware, if we do that, on the other hand, a better flow rate means more heat loss as well. So if you're thinking about heat storage, it's better to stay away from the connectivity. So in this case, it's better to drill 2 boreholes, one close the connectivity or junctions to support your flow, and have another borehole far away from the connectivities to store your heat. So if I go to here, it was the initial condition in terms of the temperature distribution before any heat recovery happens. But after 6 months of heat recovery here, you can see an area of diameter of nearly 18-19 meters has been affected, and we lost a temperature in the area we've been abstracted here, and it's getting close. You can see there is a roadways between the top part of the seams and the location we are abstracting water. So the cold water arrives here and we lose temperature, but it's not that much. But this is in a 6 months time period. But if we keep doing heat recovery for 15 more years, you can see the level of the heat loss is a lot more. You may reduce the level of the temperature until a certain level which is not efficient anymore, or maybe it's not compatible with the system you designed on the surface. The larger area, even the other layers has been affected. Nearly up to 260 meters away from your abstraction point has been affected after 15 years. So in this case, it could be a good idea to extract the waste heat and store that waste heat under the ground to top up the level of the heat to keep it as efficient as possible. And if I go to the injection point, that was the abstraction point, but this is the injection point. So when we store heat under the ground in the injection point, we can see sooner or later, all the mines, when we inject water, the temperature becomes the same temperature as the water we inject inside, because the new water pushed the previous water away and they substitute the previous water. So it's just a matter of the time and the rate you are injecting the water. And interestingly, if you see number 7 here, this is another cold seam which is far away from your injection point, 50-60 meters below your cold seams. But you can see the temperature has changed very fast because it's easy for the water to pass through the roadways and interpret to the other layers in other cold seams. And that would be a heat loss, because when it goes down, you won't be able to abstract it 6 months later when you need that hot water. Anyway, when you abstract water, usually the replacing water is coming from the same seam or something from the top due to the gravity, unless there are some specific piezometric pressure on the bottom, which is unlikely here in this area. So generally speaking, stay away from connectivities if you want to store at some point. And to conclude them, so basically we designed the model by using Petrel, Eclipse 100 and Eclipse 300. So those softwares help us to quantify the impact of different parameters. And by knowing those parameters and their impact, we can compare different scenarios to choose the best location to drill and having an optimized engineering design on the surface. And that was from me. Thank you for your patience and listening to the conference. Thanks.